Yeah, there's a very old, Miss Hine will remember, it was called Seth's Law, that she definitely disliked a lot. But Seth's Law was the integral of 6 equals 1. It was the weirdest. And people were obsessed by Seth's Law, and when they didn't know an answer to a question on a test, they would write the integral of 6 equals 1 by Seth's Law. That was like the default answer if they didn't know. So this, I thought that the Laplace transform of 7 equals 16 is kind of like Seth's Law. So that's why we are in chapter 16. But the book, Seth was a student.
Oh.
He was the one that came up with Seth's Law.
Oh, got it.
Seth looks like a very smart student.
No, it doesn't.
Well, like, you need a default answer and something to write by that looks like someone.
It sounds like you got a lot of test questions wrong. It's like instead of drawing the like writing,
It was the full Seth's Law was the integral of 6 equals 1 always.
Oh,
That's full Seth's Law. Now, so if for some odd reason Seth's out here watching my videos, you're still alive in the memories of one of our teachers, Seth. I tried to convince them when they were in Calc 3 to come up with a multivariable Seth's Law, but they never did. All right, the first thing I want to start with is an example. Because sometimes we want to find the Laplace transform of some function. We're not using the definition. We want to look it up in a table. And our function doesn't match anything in the table. So sometimes we need to do some work to our function in order to be able to find the Laplace transform. Similarly, when we end up taking inverse transforms, we end up having to do some work to those things before we can take an inverse transform. So let's say we want to find Laplace transform of 2 sine squared of t over 2. Well, when we look in our basic table and we have the Laplace transform of sine and the Laplace transform of cosine, and both of those are just sine of t and cosine of t. So somehow we need to be able to express 2 sine squared t over 2 in terms of sines and cosines. So we need to do some work on our function. So I'm going to say we know, and maybe I feel like I should modify know somehow. We know that sine squared of t is 1 minus cosine 2t over 2. Power reducing formula, double angle formula, somehow we come up with this identity. So this tells us that 2 sine squared of t equals 1 minus cosine 2t. And I know we've looked at this this thing before. This quantity, 2t, is twice this quantity. So we can say 2 sine squared of t over 2 is 1 minus cosine of t. This quantity is twice this quantity. So these two things are saying the same thing. This is actually how we get the half angle formulas from the double angle formulas. So we can say that the Laplace transform of 2 sine squared of t over 2 equals the Laplace transform of 1 minus cosine t. Yeah, that's right. 2? Yes. 2, yes. I just thought I'd left out a 2. And the Laplace transform is linear. So this is Laplace transform of 1 minus the transform of cosine t, and we can look those up, and we get 1 over s minus s over s squared plus 1. So sometimes we have to do a little work if we want to look up our Laplace transform in a table. And just another reminder, usually when you are looking at inverse transforms, so the inverse transform of this quantity would be this quantity. Usually when you're looking at this, you would have, these would all be combined into one single fraction, and you'd have to do some work to that to get it into this form to be able to take an inverse transform. So I'm just kind of previewing inverse transforms for us. And that's really how we find the inverse transforms, is we find Laplace transforms of a bunch of functions and say, okay, well, the inverse transform of this is this. Because in general, trying to find the inverse, generally find an inverse of that integral definition is difficult. In fact, finding, trying to invert functions that are defined by an integral similar to Laplace transform has led to the discovery of whole new areas of math. Not necessarily Laplace transform, but similar kinds of integrals. All right, so let's talk about what we need for, what conditions on a function do we need for the Laplace transform to exist. So because of the way we've defined the Laplace transform, the integral that defines the Laplace transform doesn't necessarily converge. There are functions for which that integral doesn't converge. For example, Laplace transform of 1 over t and the Laplace transform of e to the t squared do not exist. If we tried to integrate those functions, put those into our definition of the Laplace transform, those integrals would diverge. So we want to know what are the conditions on our function that give us the existence of the Laplace transform. So we're going to talk about sufficient conditions. We need f is piecewise continuous on 0 to infinity. And just a reminder, piecewise continuous means we have a finite number of discontinuities. And they're finite discontinuities, not infinite discontinuities. And we'll define what this next term means in just a second. And f is of exponential order. For t greater than some t. Basically what exponential order means is that f grows more slowly than an exponential function, eventually. So our definition. function f on 0 to infinity is of exponential order as t approaches infinity, if there exists we have some constants c, m greater than 0 and big T greater than 0, such that the absolute value of f of t is less than or equal to m e to the ct for all t greater than t. So what this is saying in precise mathematical terms is that f of t grows more slowly than some exponential function eventually. If f is increasing. If f is increasing, that's what we mean. And generally, that's kind of how we think of exponential order. Our function grows more slowly than an exponential function. So this grows more quickly than this exponential function because of that t squared. So this e to the t squared is not of exponential order. Positive integer powers of t are always of exponential order. So in other words, absolute value of t to the n is less than or equal to m e to the ct. Or I can write absolute value of t to the n over e to the ct is less than or equal to m for t greater than or equal to t. This means the limit as t approaches infinity of t to the n over e to the ct is finite. For n equals 1, 2, 3, dot, dot, dot. And we can see this using L'Hopital's rule. And the way we would say it kind of in everyday language is t to the n grows more slowly than e to the ct. So this is our sufficient conditions for existence. We need a piecewise continuous function, and it grows more slowly, or less than or equal to. It grows at the same rate or more slowly than an exponential function. For most of the functions we'll work with, they are going to be of exponential order. So we just wanted to include this. Because occasionally we'll get some function that behaves strangely, and we can usually look at it and say, oh, well, that function's not of exponential order. That's why we're having trouble with this Laplace transform. So our theorem for existence of the Laplace transform. So we defined exponential order. Now we're going to say if f is piecewise continuous on 0 to infinity and is of exponential order and just to reiterate, that means the absolute value of f of t is less than or equal to me to the ct for some t greater than t. Then the Laplace transform exists. For s greater than c, and that c refers to this c. And when we talk about the Laplace transform, we talk about this value of c in our exponential order definition. That's what we mean when we talk about that value of c. We often say, when we're talking about Laplace transforms and various properties of Laplace transform, for s greater than c, it's referring to the c in our definition of the exponential order for the function. So piecewise continuous, basically piecewise continuous and a well-behaved function. We're going to have Laplace transforms. For what we're doing, we're not going to do a lot with the existence of the transform. Again, every once in a while we'll run into some function and we'll be able to look at it and say, oh, it's either not piecewise continuous, or we can look at it and say, oh, it's not of exponential order, that's why it's giving us some problems. All right, so what I do want to talk about is how do we find transforms of piecewise continuous functions? Because so far we've done transforms of continuous functions. And our answer, how would we find transforms of piecewise continuous functions? We might be able to guess, based on our definition, is more integrals. So we want to find the Laplace transform of this function, where f of t is 2t plus 1 for 0 less than or equal to t less than 1, and 0 for t greater than or equal to 1. So we want to find the Laplace transform of this function. Piecewise continuous, we just have one discontinuity at t equals 1, and it's not an infinite discontinuity. So we're going to say the Laplace transform of f of t is going to be, by the definition, the integral from 0 to 1 of 2t plus 1 e to the minus st dt plus the integral from 1 to infinity of 0 e to the minus st dt. Well, for this piecewise continuous function, it's nice because that second integral is just 0. If we had some other function there, we'd have that second integral to evaluate. So we just have, actually have two integrals to evaluate here. So we get the integral from 0 to 1 of t e to the minus st dt plus the integral from 0 to 1 of e to the minus st dt. And these are not, be careful here, these are not individual Laplace transforms because our limits are 0 to 1, not 0 to infinity. So we can't just look these up because these are not Laplace transforms. together they will be the Laplace transform of this function, but these are not individual Laplace transforms. So for the first integral, we have integration by parts, which if we've worked on the homework, we see that comes up a lot in Laplace transforms. U is t, du is dt. Probably done this one before. dv is e to the minus st, and v is negative 1 over s e to the minus st. So we have 2 times u times v, negative t over s, e to the minus st, and we're evaluating that on 0 to 1, minus the integral from 0 to 1 of v du, minus 1 over s, e to the minus st dt. This gives us 2 times negative 1 over s e to the minus s minus 0, plus, when we integrate this, we get 1 over s times negative 1 over s e to the minus st, and we're evaluating that on 0 to 1. And when we evaluate all this out, this is similar to this. We end up with negative 2 over s e to the minus s minus 2 over s squared e to the minus s plus 2 over s squared. So that's for our first integral. So for the second integral, this one's easy to evaluate. We just have minus 1 over s e to the minus st evaluated on 0 to 1, which is minus 1 over s e to the minus s plus 1 over s. And I will say, be careful here, for me at least, because after doing a bunch of Laplace transforms, I find it very easy to automatically switch to 0 to infinity and not even think about the fact that I have a finite limit of integration there. After doing a bunch of Laplace transforms, it's almost automatic that, oh, it's 0 to infinity. So be careful with the limits, especially when you, if this could be 0 to infinity, and this could be 0 to something else. This could be, I don't know, 0 to 5, and this could be 5 to infinity. So be careful with your limits of integration on these piecewise functions. So finally, we have that the Laplace transform of that piecewise continuous function is, combine all those together, minus 2 over s e to the minus s, minus 2 over s squared e to the minus s plus 2 over s squared. Did I drop? No, sorry, I missed part of it. Minus, yeah, I forgot to, this is not right. I just rewrote that first part. So let me combine them together, actually. We get minus 2 over s e to the minus s, minus 3 over s e to the minus s, plus 2 over s squared, plus 2 over s squared, plus 1 over s, all together. I didn't add these things, whatever, then what do we get? Minus 3 over s, or sorry, minus 5 over s, 4 over s squared. And this is for s greater than 0. Yes.
Shouldn't we just minus 3 over s to give it a negative s? I don't think we have to.
Should be squared. First term should be negative 2 over s squared.
Oh, yes. Minus 2 over s squared. To what did I do here?
It's just next to one of those two. Yeah, just erase one of those 2 over s squares and you're good.
Which one?
You have two,
Oh.
one. You have 2 of them.
Just one of them?
Yeah, one of them is supposed to be either negative.
Oh.
Yes. There you go.
Yes.
Where do you get the s greater than 0 condition from?
What's that?
Where do you get the s greater than 0 condition?
S squared.
It's s greater than 0. It's for s greater than 0.
S greater than 0 because their denominators are s here.
But could you have, like, obviously s can't be 0, but could you have s less than 0?
If s is less than 0, then if s is less than 0, usually we say s is positive because this infinite limit, then that integral diverges. So we usually keep s positive. All right. So is all my arithmetic correct here now?
Yes.
Okay. Yeah, I think I just forgot to write an s squared somewhere. Or I forgot to write an e to the minus s on my thing. Yes.
Do we always just keep s positive then?
Well,
Yesterday we did like s.
it depends on the form of your integral. Because for some it might be s greater than some value. Generally, we keep s positive. And usually that is because if we have an infinite limit of integration and we have this e to the minus st, that integral is going to diverge if s is negative. So only converges if s is positive. All right, the behavior of our Laplace transform as s approaches infinity. If our function satisfies our conditions for the existence of the transform, then the limit as s approaches infinity of the Laplace transform is 0. All right, so just a couple of caveats now. That's the last thing I really want to talk about today, but a couple of caveats. The conditions that we have given for the existence of the Laplace transform are sufficient conditions. If those conditions hold, then the Laplace transform exists. They are not necessary conditions. So that is, there are functions that are not piecewise continuous that have Laplace transforms. And there are functions that are not of exponential order that also have Laplace transforms. So these are, if those conditions are true, then we have a Laplace transform. If those conditions are not true, it does not necessarily mean we do not have a Laplace transform for a function. If f of s does not approach 0 as s approaches infinity, we can say that f of s is not the transform of a piecewise continuous function. Of exponential order. We cannot say that f of s is not a Laplace transform. Of some function. There are other kinds of functions that we could consider that have Laplace transforms. So just because our Laplace transform doesn't approach zero, we could say it's not the Laplace transform of a piecewise continuous function of exponential order, but we can't say it's not the Laplace transform of some function. And finally, for what we do, generally we don't state the restrictions on the values of s. In most examples, we just assume that it's restricted in such a way that the integral converges. The definition of the Laplace transform, that integral converges, so that we can find the Laplace transform of a function. So for this first section, we've been saying for s greater than whatever. In general, we just assume that s is restricted in such a way that the Laplace transform exists. Okay, questions? Yes.
Did you get a haircut? It looks really good.
I did use my little shaver the other day. Thank you.
April Fools.
It doesn't look good, or it doesn't look like I got a haircut.
That's very firmly executed.
I think it looks good for
I think it looks great.
Thank you.
That's poorly executed. Yeah.